Greetings all. Welcome to this episode. This box that you see before you is the subject of this episode. And I'd like to get in a little bit about why I made this and what purpose it fulfills. So recently, a friend of mine, an old friend of mine, got in contact with me, and he had a requirement for a temperature sensor that would measure the difference in two temperatures. And if the difference between the two temperatures exceeded a certain threshold, it would engage a relay. And when the temperature fell back below that threshold, the relay would disengage. He gave me some information, particularly some websites and some other locations for literature that was a starting point to look into how to put this design together. I thought it was an interesting subject, so I decided to film the research and development aspect of this design and show you the end result of the project. So without further ado, let's take a look at some of the research material that I went into and looked at, as well as some explanations of how the circuit works. So this is the web page that my friend was referring to when he was talking to me about the temperature sensor that he was interested in working with. This is a website called Making Easy Circuits, and on this page we have a circuit for making a differential temperature detector or a differential temperature sensor. Looking at the circuit itself, it's really divided into three stages. We have a Wheatstone bridge here, providing a differential signal pair, going into an IC1, which is a 741 op-amp, and in this case they're using the op-amp more or less as a comparator. The output of the 741 goes into a high side switch, which is comprised of Q1 driving this relay down here, which has a single pole double throw output, and all this is running off of 12 volts DC. This here, P, is used to adjust the temperature differential at which the circuit triggers. It essentially is unbalancing the bridge so that these two voltages are no longer close to zero or close to the same value. What it would be is these would be a value which would be opposite to where you want to get to. And what I'm saying here is that this circuit will switch over when these two points here are very close in value and they actually transition or cross over from a summation, a positive summation, to a negative summation. So this trimmer here will be set to some voltage in millivolts that corresponds to X degrees Celsius. As either this diode heats up or this diode cools down, these values get closer and closer to the point at which they reach zero, and then their summation reverses in sign. So it becomes a negative value when you subtract them mathematically. At this point, this op-amp will flip its output state from the positive voltage rail, which is 12 volts, to its negative voltage rail, which is ground, and that will drive the transistor on, which in turn energizes the coil in the relay, and the relay will switch its output from normally open to normally closed. So getting back to the whole temperature thing, how is this thing actually measuring temperature? Well, it's using a diode as a temperature sensor by looking at the forward voltage across the diode and how that forward voltage will rise and fall depending on the junction temperature inside of the diode itself. So what do I mean by temperature and junction temperature and forward voltage? So this is a page on diode modeling, and most of this we can skip over. It's a lot of heavy math that's describing the overall effect of a diode, and as it transitions through its knee here, as you increase the voltage, its current rises. This is not really what we're interested in because this is typically graphed at a constant temperature. If we go to the bottom of the page, we can see that there's a section here on variation of forward voltage with temperature. And it does show us that there is a known relationship between the junction temperature and the forward voltage across that junction. In this particular case, they say, so as the diode becomes hotter, the forward voltage for a given current decreases. And they give an example here of a CY7, which is used as a temperature sensor in this case that they're talking about. And they discuss that its forward voltage can vary from 1 volt in liquid nitrogen, 0.54 volts at room temperature, and 0.29 volts at 100 degrees Celsius. Well, it'd be nice to see if we can get some sort of simple equation to map that. So if we look at this reference 7, which is this page here, I've stopped it at the particular point that we're interested in. We can see in this paragraph that they're saying here, at any particular current, the voltage across the silicon diode family decreases about 2 millivolts for every rise in 1 degree Celsius. So there we have our slope, and we can use this to kind of analyze the circuit a bit further when we get it on the bench. I've sketched out the schematic for the temperature sensor. I'm calling this revision 1 for reasons that I'll explain later. So you can see here, this is a more traditional schematic layout for the sensor. Here's the Wheatstone bridge with the left and right sides going into the op amp. The op amp is set up for essentially theoretically infinite gain, so it's really just acting as a comparator. It's running off of 12 volts for V plus and ground for V minus. What this means is that the ground point, the theoretical ground point, is actually halfway between these two, so it's around 6 volts. So virtual ground is 6 volts. And this is something that we have to keep in mind when we go back and analyze the Wheatstone bridge. The output is then going to this high side switch, Q1, which is then driving the relay. And I just have a common, normally closed, and normally open on the relay here. We know from our first analysis of the diode that what's happening here is that the diode's forward voltage drop is changing as the junction temperature changes. So it's not really acting as a resistor here, it's just acting as a voltage drop, a voltage reference, if you will. We'll say for now that it's about 0.6 volts. If we do one leg of the circuit, we can see that half of this resistor is being used for this leg, and then this common resistor is also being used for this leg. If we say that the current through this leg is I, the current through this leg is I, or IL and IR, and for the sake of argument, IL equals IR, then we can say that the current through the resistor here is 2I. And we know from Ohm's law that if we want to see the same voltage drop across a resistor when we have the current, that is 1I, we have to double the resistance. So here I've sketched out the left side here, and I can see 500 ohms, the 4.7K resistor, and I've doubled the 2.7K resistor to get 3.4K. Now we can do the voltage drop analysis here. You've also noticed that I'm showing 11.4 volts at the top instead of 12, and I'm taking into account the 0.6 volt drop here. What we want to know really is where the DC bias point of the left and the right are standing. So we assume IL and IR is the same, and we just call it I. And we can take a look at this circuit and figure out what I is. 12 minus 0.6 volts over 500 plus 4700 plus 3400 ohms. Punch the numbers in. We have 11.4. Let's go we have a total resistance of 8.6K. So we know it's 11.6 divided by 8.6K. And that comes out to just a little over 1 milliamp. So we have 1.3 milliamps. So let's say it's approximately 1 milliamp. If the current across R1 is 1 milliamp, the voltage across R1 is therefore 0.001 times 4.7K, which is 4.7 volts. V across RB for 1/2, we have 0.001 and 500, so we know that's 0.5 volts. So now we can take 11.4 minus 0.5 and then minus 4.7, and we get 6.2 volts. So we know that the voltage L is equal to 11.4 minus 4.7 minus 0.5, and so VL is approximately equal to 6.2 volts. And that's very close to our virtual ground point, which is important. The op-amp has a minimum, the range of the inputs cannot go rail to rail with respect to the V plus and V minus. Newer op-amps are so-called rail to rail design. They can do that, but this is an old 741. So we want to keep this bias point as close to the virtual ground point as possible to make sure that this thing is centered. So that's good. We can see that that'll work. Going back to the temperature characteristics of the diodes, as we've stated before, we know that in that diode we will see a 2 millivolt drop in the forward voltage for every increase of 1 degree Celsius. Now the nice thing about the bridge circuit is that we don't really have to worry about the absolute voltage drop for the given temperature. Because it's a relative measurement, the absolute voltage is canceled out, as it were. So the only thing we really worry about is that if we have this at a given temperature, T, and we increase this one by T prime, what is the lowered forward voltage across this relative to this? And this is really how this temperature sensor works. You don't really have to worry about an absolute temperature. You're always comparing one temperature against another. So it's always a difference in temperature and not an absolute temperature. So this equation is kind of stating that. We have the voltage, forward voltage at a temperature T is approximately equal to the forward voltage at a known temperature, the reference temperature, minus 0.002 times T minus TR. If, for example, our forward voltage at our reference temperature is 20 degrees, is around 0.6 volts, if the temperature on the right side here, VR, increases by 5 degrees Celsius, we know that the forward voltage is going to go down by about 10 millivolts. So if the temperature on the right is 5 degrees higher than the temperature on the left, the difference in the positive and negative inputs going into the op-amp will be 10 millivolts, assuming that we've balanced the circuit when both of these are at the same temperature, so that 2 and 3 are the same voltage. Now let's take a look at some of the problems with this circuit. The switchover point of the op-amp is a very small range. The slew rate is very high on this, meaning that the difference between these two inputs can only be a very, very small amount before the output will either saturate the V plus or the V minus, because the gain is very, very large. And the output, of course, is K times 3 minus 2. If K is like a million, it doesn't take much of a difference in this voltage for this output to saturate at either the maximum V plus or the minimum V minus. In reality, it doesn't actually go all the way to V plus or V minus because, like I said before, it's not a rail-to-rail op-amp. What that does mean, though, that if this temperature is very close to this temperature, or it is being skewed such that the temperature at this point is such that the voltages are very close to zero, a very small increase in temperature will turn the circuit on, and a subsequent very small loss in temperature will then turn the circuit off again. So you may get quite a lot of noise at the crossover point where it's constantly turning on and off. This is because the circuit doesn't have anything called hysteresis or dwell in the circuit. So what you really want to see is that the circuit will go to a switchover temperature, and when that occurs, the temperature for it to switch back again would be lower than the original point at which it switched on. And this leads us to revision 1.1. What I've done here is I've taken advantage of an additional input on the op-amp, which is one of the bias points. There's two pins that are not shown in the other diagram because they're normally not used. But the op-amp has two additional pins that you can use to tweak the offset between these two. So if, for example, these are tied together physically, you want the output to be at the virtual ground point, which would be, in this case, 6 volts. The way that this is done is that there are 2 pins that you can connect a potentiometer across, and you can balance out the potentiometer to zero the internal errors inside of the circuitry such that when these two are at the same voltage, the output tracks that and is actually zeroed as well. What we can do with this offset at pin 1 is we can use this to inject an additional offset when the relay turns on. So when you go up in temperature, so if this is our temperature chart and this is time for TR, we have a crossover point here where it will turn on as you go up through here. As it rises up, the output of the circuit will turn on at this point. Let's say this over here is the output. So the output will turn on here. When that happens, it changes this threshold point here and actually lowers it to a new point. So it's dropped it down by a small amount, let's say 2 or 3 or 5 degrees. So when it has to turn off again, the temperature starts falling again. This is the point at which it will turn off, not this. That means that you have to rise up through the high threshold to turn it on, and you have to go down in temperature to the bottom threshold for it to turn off. So this zone here is our hysteresis, and this prevents the circuit from rapidly turning on and off if you're right at the threshold temperature. The final part here is I'd like to kind of explain how we skew the temperature there in the first place. If we skew this potentiometer one way or another, we can unbalance the bridge to, in fact, effectively make the voltage here lower than this voltage here. So if this is lower than this is effectively has a positive output because this summation is a positive, net positive result. This is close to the positive voltage, and this high side switch is off. As this diode warms up and its forward voltage falls, this voltage at this point starts to decrease to the point at which this voltage is reached and the threshold is crossed. This summation becomes negative and the output then goes to near ground and turns the switch on. The difference between these two, if we want to know what temperature it'll switch over at, is we measure the difference between these two, and for every 10 millivolts of difference, it accounts for 1 degree Celsius that this much rise before it matches. So just using a multimeter, we can measure this difference and we can figure out what voltage difference this switch will activate at. So let's look at a prototype of this laid out, and we can play around with it a little bit and see how it works in real life. I've prototyped the temperature sensor and I've put it on this proto board. It's powered by 12 volts. It's just a single-sided 12-volt circuit. This is just some decoupling here to prevent any sort of oscillations or in the op amp, and to smooth out the rail. As the relay engages and disengages, you can get quite a bit of bounce. We have the bridge here, the left side and the right side diodes, and the balancing pot here, RB, the op amp, the high side switch, the relay, and we have two LEDs here, and they'll switch between red highlighted and green highlighted. When red is on, it's normally closed, and when green turns on, it switches over to normally open. By moving the RB, we can switch and find the 0 point. So right there is the point at which the diodes are balanced, and just adding just a tiny bit of heat to that will cause it to switch to green. The reason why it's not switching back, or the reason why it takes such a long time to switch back to red in this particular case, is that we have hysteresis on here with the diode. If we remove the diode, or the hysteresis resistor, we can see that it returns back to red much faster. I have a little trimmer back here that I can use to increase and decrease the dwell point. I'm pointing to is right there. So I can actually make the resistance higher or lower. The effect of a lower resistance is that it has a greater effect on the skew, or the dwell point. It increases. And as you can see, I can get pretty close to a point in which it doesn't actually turn back off again, because the threshold for the falling temperature is actually below the balance point, or it's so close to the balance point that it takes a very long time for this to settle out. It is possible to get that to a point below. It's not really the subject of the talk here, though, or the demonstration. So now that we've taken a look at the research material and taken a look at the circuit, as well as the prototype, let's see how the end prototype, or the box that you see before you, was put together. So I've got a DC barrel jack where the 12 volts comes in, 12 volts DC. And then there's a power light here, an LED. This is just a proto board I put together. It's just point-to-point wired. There's the relay. The relay is a 12 volt unit. And its contacts are capable of switching 125 volts AC at up to 0.6 amps. So we have power. I've marked out the front of it with some marks. The first mark indicates the the 0 point setting where both temperatures should match. So when we cross that threshold, we should hear the relay click. Every mark up from that is roughly 2.5 degrees of Celsius. So if I set it 2 marks up, that's about 5 degrees. So if I raise this temperature 5 degrees up compared to the reference on the left here, the relay should turn on. As you can maybe hear from the relay, it doesn't stay on very long. As soon as the diode starts cooling down again, the switch turns back off. So to help with that, we can increase the dwell like that. And now when we raise and lower the temperature with our body heat, we can see that it takes a little longer for the relay to turn back off. So I hope you enjoyed this little demonstration and project. I hope you learned something from it. We could in future do another project like this, only a microcontroller based alternative to this design. So we can support things like programmable maximum and minimum switchovers, as well as readouts for both the high and low temperature. If there's any interest, let me know in the comments, and I will put it in the queue of upcoming projects. So for now, that's all I have. Hope everybody's doing okay, and take care.